But yeah, I'd like to introduce our first speaker and the CEO of Essential, Liesl Eichholz.
All right, hey everyone, good to see all of you here. I think it's mostly familiar faces, so thanks for coming and joining us. Yeah, I'm just going to introduce imperative and declarative approaches to blockchain design, explore the current imperative model, and talk about declarative approaches to blockchains in general, and more specifically, declarative blockchain designs themselves. So most of you probably will have heard of the imperative and declarative programming models as a computer science fundamental in general. So we'll start out just going over the basics. So the imperative programming model in general, these programs express how a problem should be solved. So developers are outlining instructions and an algorithm basically to be executed step by step. So these prioritize instructions over the outcome itself. And these kinds of programming languages include things like Java and C++. On the other hand, declarative programs express what a program should accomplish as opposed to how. So developers specify a specific desired outcome without actually dictating how the outcome should be achieved. So it prioritizes the outcome itself over the instructions. And examples of these kind of languages include SQL and Haskell, and obviously our new declarative programming language, Pint. So what is the current state of blockchains today? Every blockchain today pretty much is imperative, and at least since the advent of Ethereum as the first general purpose smart contract chain, imperative programming has been the prevailing paradigm in the blockchain space and in blockchain development. And the model that this necessitates is that users have to interact with the chain via imperative instructions instead of declaring their desired outcomes in a declarative format. So most of you probably would have heard of the vending machine analogy for smart contracts. This is quite an imperative model. And basically what it is, it's a simple example of a self-enforcing smart contract or self-enforcing contract. The philosophy behind this is that blockchains should be places where contracts can be enforced and automatically executed without the need for a trusted intermediary. And the sort of stated philosophy of chains like Ethereum is that these chains should deterministically execute unambiguous code. And the problem is that the code itself is unambiguous, but the results aren't actually ambiguous because these smart contract vending machines exist within systems that have a lot of ambiguity around them. So we can extend the vending machine analogy to look at why this is a problem. So say you go to a vending machine and you want a bag of Doritos. You walk over and you look at the slot, select the slot that says Doritos, and then you insert your money. So in the blockchain analogy, this is when you have initiated your transaction and sent it to the mempool. But then you're stuck waiting for your order to be processed, and all of a sudden you see someone come along and open the back of the vending machine and replace everything out with just an entirely different item. So now all the stock is gone, there's no more Doritos, and your transaction is still processing. So what happened here is that this entity was able to change the state of the vending machine after you submitted your transaction, but before it had actually been executed. And this is obviously unintended behavior on the part of the system, but something that just emerges as a result of the design. So then finally, the instructions that you entered are actually executed, but you don't end up getting what you wanted. Importantly though, you do get what you asked for. And that's a problem in these systems, is that you're actually not able to ask for a bag of Doritos. The system has no way of conceiving of what that means. So all you can do is say, I would like the item in, slot A2, please, and just hope that by the time your transaction gets executed, that the state of the blockchain matches what you anticipated when you submitted that transaction. And this is because imperative systems have this execution-based model where there is this concept of an intermediate state between block A and block B. And during the process of this intermediate state, things can happen and anyone can come in and do certain things that mean that the state gets modified in ways that users don't necessarily expect and can't anticipate. So we're all familiar with this as the dark forest. And originally, this is an unintended side effect of imperative blockchain design. But for the people who make money from this today, it's actually no longer a bug. It's considered quite a feature. And there's now, as we all know, an entire industry that's dedicated to basically messing around with the vending machine and taking advantage of users who don't have the power to control how the vending machine works. So what we think at Essential is that this shouldn't be possible. And I don't think that's a radical claim. Most people in the space are looking at ways of mitigating MEV and thinking about how can we prevent this from happening, because it is unintended behavior. And actually, if you look at the Ethereum yellow paper, it specifically states that users should be able to interact with the system with absolute confidence in the possible outcomes. And we know that that's not the situation we live in today, but that is the ideal. And you'll notice that word outcomes, it ties very neatly back into the declarative model that we were talking about before. So if there's all these problems with the imperative paradigm and we do want to focus on outcomes, why haven't we used a different approach? People have been asking this question for a while, and since sort of 2018, there have been conversations about declarative smart contracts and how we can implement these kinds of things on existing systems. But despite the discussion happening over the course of the years, it never really took off until around early 2023 when the primitive of intents was introduced and really started being spoken about more within the space. And as I'm sure most of you know, the core principle of intents is basically allowing users to sign over their intended outcomes declaratively, so in terms of the outcome itself, rather than in terms of the imperative instructions that they want to be executed. But there's a problem with these systems, which is that they still settle on imperative state machines. So at some point along the transaction flow, you have to turn these... hold on, sorry, that just like really bright on my eyes. You have to turn these outcomes back into instructions in order to achieve settlement. So these projects actually still have to work under this fundamental vending machine model. All they do is they introduce the role of a solver, and they allow you to basically delegate the job of interacting with the vending machine to someone else. This means that the risk of unintended consequences and losses still exists. You're just handing it over to a separate counterparty. And there are a lot of projects in the space that are working on making progress here by building systems where that risk of losses doesn't get passed back to the user. It actually now sits with the solver. But the fundamental problem still remains, which is that somebody has to eat those losses, and there's always going to be people who are trying to manipulate the system. It's just passing the issue onto someone else. And you can see that with the example here of how intents have fit into the transaction order flow, where fundamentally the vending machine imperative state machine model still prevails, and all you're doing is adding extra entities into that flow. So if we accept that this vending machine model is something that we can't defend against people who want to exploit it, then what do we do instead? So we propose that we just get rid of the vending machine entirely and pick a new model. We now have these agents called solvers that are sitting there all, ready to ingest users' outcomes and do something with them. So why don't we use those to their fullest extent? And with that, we propose the concept of fully declarative blockchains. And so these are blockchains that leverage constraints to achieve state updates without the need for execution. So basically with declarative blockchains, there is no concept of an intermediate state between A and B, where people can come and tinker with the vending machine. In fact, the entire vending machine doesn't exist. State is just updated atomically. So you go straight from state A to state B. And the way that this happens is that there is no concept of on-chain execution. In fact, there's actually no in-protocol conception of execution at all. The declarative model means that execution can be removed completely, and everything can be defined in terms of constraints on state. Okay, so the declarative blockchain flow, how does this all work? How does it tie together? So every step in this flow, rather than switching from declarative back to imperative, as current intent systems do, stays declarative the whole way through. So first off, users submit their intents declaratively in the form of constraints. So they're expressing, this is the outcome I want, not how to achieve it, not setting any instructions. And users within these systems are able to directly constrain state that they own, and this can actually be enforceable on-chain within the system. Then you also have the concept of smart contracts becoming declarative. So developers are writing their smart contracts declaratively. These also just consist purely of constraints on state. Rather than being instructions to call specific opcodes, smart contracts just consist basically of rules that say what is and is not considered a valid new state. And these, again, are enforceable on chain. And finally, the state machine is also made declarative. So what happens in this flow is solvers can ingest all of these intents coming in from users. They can search for the best solutions, and that searching, importantly, all happens off-chain, which means that it's not an in-protocol part of computation is not in protocol. And then those solvers can just directly propose their solutions as state updates. And this means you don't need anything like an execution VM. So declarative blockchains can just have a constraint VM. This is responsible for checking constraints and basically making sure that any new proposed state doesn't violate any other constraints that have been expressed, which means that all of the heavy stuff, the computation and calculation of new state, can happen off-chain, and it makes the chain very lightweight. But it also means that you don't need anything like ZKs to move compute off-chain, because the compute itself is not what you need to determine what is a valid new state. And if you think about this in the context of what we're trying to achieve with blockchains, they're distributed ledgers. And with a ledger, what you care about isn't how you get from A to B. You just care about the state of the ledger. So the constraint-based declarative model really makes a lot of sense when you're thinking about not how do you get between the states, but just what is the new state itself. So really, we don't care about computation specifically. It's just been a necessary evil so far to make sure that everyone can agree on state. But yeah, with the constraint-based model, we don't actually need this. So now, instead of state updates just being a side effect of execution, they're actually just atomically and declaratively included. So obviously, anyone who's familiar with the intent model or declarative model knows that there are a lot of benefits of this. Existing intent projects have already seen a lot of these benefits come to light for users. The main thing on the user side is just the optimality of outcomes. Now you can actually express the outcome you want and guarantee that it gets included, and so you don't have all these unintended side effects. There are a handful more great UX improvements for users as well, but the fundamentals of the declarative model are that it really enshrines everything in terms of the outcomes that the user wants. On the developer side, basically you're able to build arbitrarily complex applications because you don't have to understand the idiosyncrasies of a VM or optimize for lowering gas costs or anything. All you have to do is optimize for lowering the number of constraints that have to be validated, because the only thing that happens on chain is the constraint checking and within the constraint VM. But the complexity of the applications themselves can be arbitrarily high because that stuff is all out of protocol and therefore doesn't contribute to higher costs within the protocol. The other thing about the developer experience is that it's actually much more easy to build secure code because you don't have to understand the underlying VM in order to really make sure that there aren't any bugs or loopholes that can be exploited. And then for the Web3 space as a whole, this just has major scalability benefits where you can massively increase throughput because constraint checking is much cheaper than actually executing the chain. So for validators like clients and also new people coming into the system and trying to sync the node, you don't have the system where every single transaction needs to be re-executed for all of time for anyone else who wants to join the system. So how are we doing this at Essential? A quick self-show here. We are building the first declarative blockchain, and we're basically aiming to take this paradigm out into the world and encourage other people to use it as well. Alongside Essential, we have just released Pint, which is a constraint-based programming language. It's designed for building declarative blockchain applications. You're going to hear a lot more about some of those things today, so I won't go too deeply into them now. But yeah, suffice it to say, there's a lot to look into, and check out what we released earlier this week and what we've built, so you can dive deeper into the declarative blockchain concepts and start playing around with it a little bit more. So that's basically the call to action. I encourage everyone to build declaratively, start thinking declaratively in the context of blockchains. Where we're at right now in the context of declarative blockchains is still pretty early, but I hope everyone can take some inspiration from today and try to start building in a declarative model. So throughout the rest of the day, you're going to hear more from a lot of teams in the space that are building declarative projects, either with intents, declarative blockchains, and everything in between. You're going to hear a lot of different perspectives on how people are thinking about this paradigm. And yeah, also hear a little bit more from our team about our declarative blockchain and Pint as well. So we ultimately think that the declarative model is going to be the future of blockchains. And yeah, we hope that everyone here is going to get excited about it and join us on the journey. So thank you, everyone. Welcome to Declarative Day. And yeah, looking forward to a great day with you all. We've got a bit of time for questions, actually. So if anyone wants to...
How does native account abstraction work in the declarative paradigm? Like, what's the role of account abstraction in general?
Yeah, so basically there's no distinction between, or no meaningful distinction between like EOAs and smart contracts, basically because, once again, like users can define their interactions in terms of constraints on state, and smart contracts are just constraints on state. Basically, like every user-owned account just becomes like, is able to be a smart contract. So when a user deploys an intent, they can actually deploy that on-chain, and it's able to just sit there and like wait for solvers to pick something up when the state it gets updated in a specific way that enables it. So I don't know, a sort of vanilla example of this is something like a DCA strategy, where like rather than having to actively like call a function in order to have something like that execute, it now is able to sit there and solvers can see when that when the conditions for those constraints are met, and are able to just like update that state automatically without user interactions. So that's sort of a concrete example of how account abstraction can work.
Is that like going off of the 4337 standard, or?
So it's not directly based on the 4337 standard at all, because the system has no conception of the EVM or any execution VM. It's really just an emergent property of a declarative architecture itself.
Do you anticipate like solvers are going to be mostly leaving this chain to go source liquidity from another chain and come back, or are you going to try to build up liquidity vertically on this chain?
Yeah, so the question is, are solvers going to source liquidity from other chains, or are they going to have to source it from on the chain itself? So fundamentally, with this model, you can obviously only constrain state on the chain itself. That's the only state that can be constrained within the system. So solvers will have to pull either from liquidity that is on chain, so that could be like in an AMM, in a lending contract, whatever it might be, or can provide their own inventory. So we anticipate a lot of solvers also being market makers, which I'm sure a lot of people are going to talk about today. But yeah, basically we'll have to manage their own inventory on chain. Should we? It's time for a couple more. Yeah.
So what is recorded in the chain, and what kind of consensus mechanism do you use?
So yeah, I mean, what's recorded on the chain is it's an account-based model. It's very similar to like what would be recorded on like another chain, like Ethereum, for example. And the consensus mechanism, so we're deploying as a layer 2 on Ethereum as the initial sort of iteration of this. Initially, we'll probably end up launching with some kind of like centralized sequencer isn't the right word, because the job of sequencing is actually performed by solvers, and ordering transactions or state updates rather is something that is done based on the most optimal solution rather than some kind of like arbitrary notion of how can we extract the most value. So yeah, the initial version will have a centralized entity that is posting state updates to, or posting blocks to the L1, but eventually we're going to have a decentralized validator network that will likely use a version of Comet BFT.
Since the majority of the compute is happening off-chain, how do you ensure the verifiability and provability of the operation that is being done off-chain?
Yeah, how do we ensure the verifiability? So this is kind of a challenge of like moving your brain into the declarative model, because like there is no concept of execution itself. What happens is, like as I sort of mentioned in the talk, state is like directly proposed by solvers. So the new blocks will just be a like new state that's proposed, and then you actually work back from that to validate the constraints and make sure that none of the constraints that have been set were violated. So basically, solvers are empowered to propose any state update that fulfills all of the constraints that have been set by users and contracts on chain. So there is actually no need to verify any of that compute, because the compute is just figuring out, like, you know, what would be the optimal solution that I can propose. But that's something that is internal to solvers. And what actually ends up happening, like in protocol, is that the constraint checking makes sure that the solutions are valid without actually needing to figure out that compute component of getting from A to B. Yeah, Robbie?
If there's more than one sequence of transactions that solves these constraints, how do you choose which solver is the one that wins?
Yeah, so how do you choose the winning solver? So what we anticipate is that actually any given intent will have like a bunch of different solutions that get proposed by solvers. So you can imagine if I say try to initiate a swap, that one solver will come in and say, oh yeah, I can fulfill that from this liquidity on this particular AMM, or I can like fill that myself. And so solvers are aiming to competitively provide like the best possible solution for the user. And there's actually an objective measure of what the best possible solution is, because as part of the user setting their intent, that is just purely made up of constraints, they can set like an objective utility function that says, you know, this solution is objectively better than this solution for me. And so then once solvers have all proposed these solutions, there's a sort of like a commit reveal stage. So solvers propose solutions, then they all get revealed, and then solvers collaboratively come together to try and build blocks that have the highest aggregate optimality for users. So if you have a situation where there's like a bunch of possible solutions for a specific intent, then the one that is objectively meets the user's utility function will be selected. And obviously there will still also be some cases where there are like state conflicts where you know, two solutions are trying to like pull from the same state. So in most cases, we anticipate that there will be other solutions available. So let's say one solution pulls from like a specific AMM that moves the price on that curve. Then instead of like putting another solution for a different user that pulls from the same AMM, there will be, you know, another solution that pulls liquidity from a different place. So there's, you know, a lot more like a lot wider of a solution space to make sure that you don't have to like pre-commit to any specific interaction before like the full state of the block is determined. So there's a lot more like optionality there as well.
How frequently are blocks included in the network, and how are you bootstrapping the solver network?
Yeah, okay. Question is frequency of blocks and bootstrapping the solver network. So block frequency, we don't have a particular number yet. It's a bit of a challenge there. You have sort of a trade-off between like latency and optimality of solutions. The more time that you give solvers to find optimal solutions, then the higher the likelihood that they'll be able to get something. Realistically, when you're doing something like you know, trying to find solutions for a constraint optimization problem, it'll be on the order of like maximum sub 15 seconds for some of the like more complex things. But you know, like that's still quite a long time in the context of chains. So we obviously want to get that number down, but that's a sort of upper bound. But yeah, again, you know, still figuring out the trade-off between latency and like optimal solutions. And the other thing was solver bootstrapping, you said. So yeah, we're already in you know, a bunch of people in the audience. Solvers are here. We're already chatting to a bunch of people about you know, getting in and starting on Essential. We're also probably going to bootstrap our own solvers, and also talking to like market makers about them coming in and providing liquidity directly and providing solutions. But another sort of core route for solver bootstrapping that we see is that applications, when they deploy, will also run their own like mini solvers, so that when intents come through that aim to interact via their application, that there will be like easy solutions for them to propose until the larger solvers sort of pick up their application and start solving for it. So that also provides a potential revenue source for early applications to like, you know, be basically the only one solving for their application, and it gives them a chance to bootstrap their own applications as well until it becomes more popular and other people start solving for it. All right. Thank you, everyone. Hope everyone has a good day. Yeah, enjoy Declarative Day.